introduce Professor Bilge Yildiz, and she has a background which you can read about in the biography, also a recipient of many awards. But the title of your talk is Electrochemical Ionic Synapses for Energy-Efficient Brain-Inspired Computing.
Thank you. Thank you for the introduction, and thanks a lot for giving me the opportunity to come here and share some of our work and also to be able to discuss with you. So, yes, the title of the talk that I will share is Electrochemical Ionic Synapses, which we use for emulating the functionality of biological synapses, to some extent at least, that can ultimately enable energy-efficient AI hardware. And before I go into the talk, let me acknowledge also the team that has done this work, and we continue to push it together, and of course including my PhD students and postdocs, Mantao, Miranda, Xiaohui, Peter, and Konstantin. And together with our electrical engineering colleague Jesus de Lamo and his student Murat in the downscaling of devices, my colleague Julie on materials, and my colleague Michael Fee on neuroscience studies that he does that motivate us to try to emulate some of his findings in hardware. So why do we care about electrochemical ionic devices for computing? As many in the field, we are also motivated by the ever-increasing energy consumption and CO2 emissions in AI. And I'm also with the nuclear engineering department, that's my formal training in fact, and until recently, like as of a few years ago, I would joke that you need a small modular nuclear reactor to go with every machine learning algorithm to recognize blurry images. And it's no longer a joke, or like later this past year, these big tech companies have been literally racing with each other in buying and investing in nuclear energy to power their data centers, which are of course consuming already hundreds of terawatt hours per year in the US, and it's projected to exponentially grow. So it is a serious problem. It's already, the data center power consumption is about 4% of electricity consumption in the US, and it's projected to grow. So it is a serious problem. And if you look at this plot generated by the decadal plan for semiconductors by the Semiconductor Research Consortium, and I'll present a simplified version of it, by 2040 or so, we are supposed to consume all the world's electricity production to computing, if the real data goes like this. And of course, it's not viable, it's not sustainable. The field is after improving the energy efficiency of computing by many orders of magnitude. There is a very ambitious target of 1 million-fold improvement in the energy efficiency of computing that we all need so that this situation becomes more sustainable. And of course, one needs both algorithmic and hardware advances to get us there. And my research touches the hardware materials and hardware devices aspect of this problem. And one platform that the field is considering that can substantially reduce the energy consumption of machine learning is physical neural networks, which brings together the processor and memory in one unit, and therefore eliminates this von Neumann bottleneck of data shuttling between the two units, and can result in substantial energy gains. And these are pretty much crossbar arrays, so physical hardware crossbar arrays, where these arrays are supposed to emulate the connectivity of neurons, and their cross points that are referred to as programmable resistors or memristive devices are supposed to emulate some functionality of the synapse depending on the aim of the physical neural network. And these devices are non-volatile random access computer memories that work by changing the resistance of a material. So the resistance depends on the electrical history that you apply on the material. And these conductance states or resistance states that you obtain can train and obtain can serve as node weights in a physical neural network. So for example, you have a given device or a material, you send a number of voltage pulses that can give you a number of conductance states, ideally in a continuum, discernible states, and this should be reversible. That allows you to get these node weights in the training of the physical neural network. There are a few established mechanisms of modulating the resistance through this memoristive behavior. So the top two I sketch here are referred to as filamentary mechanisms, where in the first one you have a metal electrode and a solid electrolyte insulator, and you apply electric field across the electrolyte and electromigrate the metal atoms, and typically they form dendritic structures. Depending on the morphology of this dendrite or filament, you can get multiple conductances. And in this case, you again apply electric field across the layer. Now you electromigrate or extract oxygen out of an insulating metal oxide. And when you are dealing with oxygen, which is very slow at room temperature, you also form dendritic structures for the diffusion path and leave behind electronically conducting zones or electron-rich zones that can also give you modulatable conductance depending on the structure of these dendrites. So these are rather simple structures, two-terminal, but the formation of these filaments is highly uncontrollable, very difficult to control in practical structures, and compromises the reliability in the training of these devices. The third one that I sketch here is based on phase change of a given compound between insulating and conducting phases induced by Joule heating. And the challenge here has been it's not as low energy and suffers from drift of the programmed state. And the fourth one is a more recent mechanism that has attracted our attention as well as other colleagues in the field, is electrochemical shuffling of ions from a reservoir into a target material and back. And the ions bring together electronic carriers that can serve as doping of the target material that allows us to modulate the conductivity. So what we refer to as electrochemical ionic synapses rely on this mechanism, which I will tell you more, and it's not filamentary, it's much more controllable and reliable. So before we go into the materials and the underlying mechanism for this device, let's have a look at what the biological synapse does. And of course, I'm not an expert on this, but the two key things that I would like to highlight is that the electrical signal transmission ease, so conductance of the synapse, can change permanently depending on the electrical history, which is referred to as potentiation, long-term potentiation, if the conductance is increasing, or the reverse of it, depression. And not only that you get a net change, but the synapse can have a range of rich dynamics, nonlinear behavior. For example, the increase or decrease and the extent of increase or decrease can depend nonlinearly on the timing of voltage spikes that arrive at the pre- and post-synaptic neurons, referred to as spike timing dependent plasticity, and there are different functional forms of this local learning rule, which arises from the nonlinearity of the synaptic behavior. And in the synaptic conductance changes, transmission of small cations across the synaptic connection, across an electrical potential difference, is involved, which then trigger reactions with other neurotransmitters that results in the change in the conductance. But small cation transmission across an electric potential difference does exist. And the biological synapse does this synaptic potentiation or depression with energy consumption on the order of femtojoules per synaptic event. So our question was, can we emulate some of these ionic processes, but in inorganic materials that are conducive to making devices with? And transport of ions, as well as redox reactions that I will share, does give us the ability to emulate some of this nonlinearity, which is important for capturing biorealistic learning rules at the synapses. And we are familiar with how to shuttle small cations electrochemically in fuel cells, electrolyzers, batteries, and we are not necessarily limited to the neurotransmitter cations as in the synapse, but we can also look for smaller ones, larger ones to work with depending on the target properties that we are interested in. And so the type of devices that we do this electrochemical shuttling to emulate some of these synaptic functionalities are nothing but miniaturized batteries. So we have a battery where we have a reservoir where we store the ion, and if you choose that material appropriately, that can also be the gate of this electronic ionic device. You have a target material adopting from the transistor terminology that is the channel, but it's like the cathode of your battery, separated by an electrolyte. And most of the work that I will show you is with proton as the working ion. So in such a device, then we store proton in the form of hydrogen in a solid reservoir. And as we apply positive potential, we oxidize hydrogen to proton that migrates through the electrolyte, and the electrons take the outer circuit, and they arrive at the channel. And if you have chosen the channel material appropriately, the electrons can be donated to increase the electronic conductivity of this channel material. For example, if we look at tungsten oxide, which is a semiconductor with about 2.8 eV bandgap, the electrons brought together with the protons are donated into in-gap states associated with tungsten. They form polaronic carriers and increase conductivity. So every proton brings an electron that contributes to polaronic conductivity, as an example. Okay? And again, if you choose the materials right and the device geometry appropriately, I will show you that you can get really low energy and even lower than the biological synapses in leveraging this conductance modulation mechanism. And of course, after you bring the protons and electrons, if you float the gate or open the circuit, electrons cannot go back, therefore protons cannot go back, and therefore you can get non-volatile behavior. I will show you later that you can also get volatility, which becomes important in some of the more biorealistic learning rules that we aim to capture. So we have focused mostly on proton, as I said a few minutes ago, because it's the smallest ion in solid state, which gives it higher diffusivity, especially in the channel materials that we're exploring, which then, of course, correspond to higher operating speed that comes with lower energy cost and also least disruption to the material that we are inserting into, which are advantages compared to other small cations, like lithium or sodium or magnesium. But with hydrogen, you need a reservoir where you can store it in solid state, and ideally also it should be the gate for your device. And for this, we have adopted a metal hydride, for example, palladium hydride. Palladium likes to absorb hydrogen at large quantities, and it's still metallic, so this serves both as a closed system hydrogen source as well as the gate of the device that we want to control. For the channel, the target material, there are a number of binary oxides which intercalate small cations, such as tungsten oxide. I will show you others theoretically in a few minutes. And the challenge is the proton-conducting electrolyte. The best proton-conducting electrolyte at room temperature is a polymer called Nafion, and that was our first demonstration system. But when we attempted to downscale these devices, Nafion is not conducive to it using conventional CMOS nanofabrication approaches, so we had to move into insulating oxides like dielectric hafnia, zirconia, and silica, which are conventionally not proton conductors in their lattice, but I will show you how we make them just enough proton conductor. So this is an expanded view of the modulation of the states, where we are sending positive gate voltages that carry protons and electrons from the reservoir into the channel, and after every pulse, we increase the conductance in increments. And of course, you're not limited to just few pulses. Here is an example of 1,000 pulses with 1,000 discernible states, which come with increase in conductance as we insert protons and reversing the conductance by extracting protons and electrons out. And getting this type of behavior very fast with very low energy is what's needed for hardware deep neural networks in the near term. And again, if you look at tungsten oxide, it's a very sensitive material to hydrogen in the low concentration regime. So up to a few %, you can get more than 2 orders of magnitude increase in conductivity, and that's more than sufficient for the purpose of hardware DNNs. And in this first work, we have found that you can indeed get to very low energies per micrometer of device, about 3-4 femtojoule per state. But we were working with rather coarse voltages or pulse parameters. And if you can fine-tune the conductance down to nanosiemens, which is also the target for the field, we projected that one should be able to get order of 10, 20 attojoules per programmed state for a micrometer device. We couldn't show that with Nafion because we couldn't really downscale it. And we had to move into those inorganic conductors, as I will show you in a minute. But again, going back to tungsten oxide, as I showed theoretically at the beginning, the conductance modulation is by donating electrons that are brought with the proton to in-gap states. And you can see from the valence band comparison of the hydrogen-free tungsten oxide and hydrogenated or protonated tungsten oxide, we see the filling of these in-gap states associated with tungsten 5D-T2G states. You can also see it in the tungsten oxidation state decrease from only 6+ to 6 and 5+. And as we increase the hydrogen content, there is also an increase in the symmetry that contributes to increased mobility. So pretty much hydrogen serving as N-type dopant that we are electrochemically controlling. And how do we get these devices to be miniaturized so we can see their limits of speed and energy? And as I said, while Nafion is the best proton conductor that we have at room temperature to date, it's not conducive to scaling down. And we had to move into inorganic potential conductors. But there is no good proton conductor at room temperature, that's period. But there are a few candidates that we could work with that become just enough proton conductor for us to work with. So the first one here is phosphorus-doped silicate glass, abbreviated as PSG. So this is pretty much silica that the CMOS field knows how to work with. And we could scale this down to about tens of nanometers, so 30 nanometer channel width, each functional layer 10 nanometer thick. And in this miniaturized device, we could again obtain more than an order of magnitude change in conductance, which is consistent with what's desirable. And we could push it down to nanosecond programming speeds. So 5 nanosecond was our limit. And in this miniaturized device with so short pulses, we could also obtain our projected extremely small energy consumption of about 15 attojoule per programmed state. So that's very exciting, but it's not the end of the story or the challenge, as I will highlight in a few minutes. And interesting to note, which I will also come back to later to leverage, is the behavior of these devices where we are electrochemically trying to push ions or protons through is strongly nonlinear with applied voltage. And if you look at changing conductance as a function of programming voltage and programming time, we see a hyperbolic sign dependence on the field across the electrolyte. So we are dealing with, in this geometry, field-accelerated proton transport through the electrolyte. If you go to much thinner or better electrolytes, we can run into the same behavior for field-accelerated charge transfer reactions or redox reactions. And we will come back to this also. So silica is not the only inorganic system that we can work with. We have also demonstrated very good behavior with thin film hafnia and zirconia, where again we get potentiation and depression by sending protons in, extracting them out. There is good retention between pulses, and again, strongly nonlinear dependence on the voltage that we apply. And as I said at the beginning, these are not filamentary devices. We are dealing with ion intercalation. Therefore, the repeatability of the behavior cycle to cycle and also device to device, which I'm not showing here, but you can ask me if you like later, is really good and already meets the targets for hardware DNN applications. So these inorganic electrolytes, like silica, hafnia, zirconia, as I said, they are actually not proton conductors in the lattice. They are dead insulators, but they become proton conductor if you make them bad. So disordered, low density, ideally at the border between nanoporosity and low density. And they become proton conductor in this microstructure because the low density regions or nanoporosity can absorb or adsorb water, OH groups, and that becomes the path for proton conduction. And so ideally you need the lowest density and finest nanoporosity to improve the proton conductivity of these type of microstructures. And we are working in that direction. So let's go back to the channel and what other alternatives do we have here. I already mentioned this briefly. For tungsten oxide, it's a semiconductor. When we insert hydrogen up to a few %, it serves as an N-type donor, which fills shallow in-gap states and forms large polarons. If you continue to increase the hydrogen concentration above 10%, the electronic structure is delocalized electrons, so here it's no longer very sensitive. You want to stay in as low concentration as possible. And tungsten oxide is what we have most experimentally experience within this device, but there are other intercalation oxides that we are theoretically and experimentally assessing now. These include vanadium pentoxide, molybdenum oxide, tantalum pentoxide, and in comparison to this tungsten oxide, and all of them form polaronic carriers when you insert hydrogen into them. So polaron trapping or binding energy is negative in all of them, so we can leverage the same type of mechanism in these other intercalation oxides and not just tungsten oxide. But then you have to see whether these polarons are conducting enough, and there is a target migration energy for these polarons to give us the right conductance range to work with. And among these different oxides that we have surveyed, tungsten oxide and molybdenum oxide put us into that range, at least theoretically. Tantalum oxide is too high barrier and not conducting enough. And in addition to polaron mobility, one also has to pay attention to proton mobility so that the response is as fast as possible. And the target is 0.3 eV or lower for proton migration barriers. And we omit tantalum oxide because it's not a good polaron conductor. But then if you look at the migration barriers for protons in the presence of polarons, which could be trapping sites, the migration barriers for tungsten and molybdenum oxide are close to this targeted 0.3 EV migration barrier. Therefore, we think both of these are potentially promising binary oxides for channel in these oxides. Okay, so we are exploring these materials that we think can become proton conductor in those ugly defective microstructures. We're exploring binary oxides that could be intercalating protons and what are their mobilities. But what are the target properties to get certain energy, speed, and programming voltage from these devices? So I've shown to you that with protons, we could get extremely low energy, so tens of attojoule per state, very fast, nanoseconds of programming speed. But probably in the fine print, what you didn't notice is the very large voltages that we have to apply to accelerate the protons through these not good conducting electrolytes. So one has to go to like order of 8 to 10 volts at present to get to these speeds. We have similarly explored with magnesium as the working ion. You can work with small voltage, so 0.5 volt, but of course then you have to wait very long for the response, like tens to hundreds of milliseconds. So the goal is to be able to stay in this nanosecond regime, but program with very low voltage, so 1 volt or less. How do we get there with these electrochemical ionic devices? We don't know what those materials will be, but one has to identify what should be the ion conductivity of the electrolyte, what should be the charge transfer kinetic coefficients at the interface, and ion diffusivity in the channel, so that the device response, which involves a rise after, of course, programming voltage and a transient to settle, can take place within less than 100 nanoseconds, which is consistent with the overall update of the network. So how do we get there? And for this, we have constructed a physical 1D model, equivalent circuit model of these battery-like devices, where we are considering the ion transport with field enhancement, of course, interface charge transfer reactions, as well as ion diffusion and conductivity modulation. And the models we adopt for these circuit elements come from existing literature, the well-established field-accelerated ion transport. For interface reactions between an insulator and a semiconductor, there is no well-established charge transfer model. So just to start with, we have adopted the Butler-Volmer kinetics. And of course, ion diffusion reactions and effect on the semiconductor conductivity, all included in this model, to map out what should be the electrolyte conductivity, interface charge transfer coefficient, and channel diffusivity for any ion, so ion agnostic, to put us into this tens to hundreds of nanosecond regime. And that's the star here. So if we summarize the found properties, we see that the electrolyte for any ion that you want to work with should have conductivity more than 0.1 millisiemens per centimeter. The charge transfer coefficient or exchange current density should be greater than 0.1 amp per square centimeter. And the ion diffusivity in the channel should be greater than 10⁻⁹ square centimeter per second, so that we can program with nanosecond and with 1 volt. So for any ion that you want to work with, these properties you don't have a material set that simultaneously satisfy these targeted properties. So these are targets for the material science to push the understanding and design of materials to reach these targets. For protons, we are working on this, but it doesn't exist. So I think this is the most challenging for protons compared to other ions. This interface charge transfer coefficient is not out of this world. This exists in HER literature, but again, how to translate that to a solid state device is a challenge. And this is relatively easy. This already exists. So these two are targets for material science studies to push the limits to get to those targets. Okay? All right. So that's for get me the conductance very fast with low voltage and extremely low energy. That's near-term hardware DNN context. But because we are working with ions, ion transport, electrochemical reactions, there is strong nonlinearity, rich nonlinearity of these devices that we can also leverage to emulate some of the nonlinearities known and shown in local learning rules, like the spike timing dependent plasticity that I have exemplified at the beginning. So if we look at the order of magnitude of this nonlinearity, we can see here that, for example, if we double the programming voltage from 2 to 4 volt, we come with a speed up of about 60-fold. If you triple it, it's 1,000-fold acceleration of the response. So it's strongly nonlinear, and as I said earlier, this comes from the nonlinear dependence of ion transport on the field across the electrolyte and nonlinear dependence of electron transfer reactions on the field at the interface. So we can leverage this nonlinearity to emulate some of these nonlinear learning rules, like spike timing dependent plasticity that comes with different functional forms. And to emulate this, we have come up with a simple local circuit which involves an equal resistor voltage divider, which essentially superimposes the presynaptic and postsynaptic voltage spikes to be applied on the synapse that we want to get this type of nonlinear behavior out of. And I won't go into the details, but again, since we have a physical model of these devices, we can deterministically design the voltage form to give us the targeted nonlinear response. And here is one example where we have this form of the pre- and post-synaptic signal, which we overlap or superimpose with that circuit I have shown to you, where the learning rule of this typical spike timing dependent plasticity is achieved by these ionic devices. And it's not only this mostly referred to or most well-known STDP form, but different parts of our brain apparently implements different types of nonlinear learning rules. They are all under the umbrella of spike timing dependent plasticity, because the x-axis is always the timing of spikes that come to the pre- and the post-synaptic neurons. And again, depending on what learning rule you want to emulate, you can design the voltage spike forms accordingly and obtain the different learning rules that are associated with different parts of our brain. So it's flexible, it's adaptable, and the timing response is also tunable. So the biological process is on the order of tens of milliseconds, but of course you want to get computers with this as fast as possible, so it's tunable down to nanoseconds with these devices by voltage as well as electrolyte geometry. And very importantly, like in the DNN case, it's much more repeatable, controllable compared to other attempts of this STDP in the field, for example, with resistive switching, phase change, ferroelectric tunnel junction, or ferroelectric FET, which are all attempted in the field, and sometimes you look at the data and you can hardly see the form, and therefore the variability of those other attempts are much higher than what we can achieve with this ion intercalation electrochemical device. So it's controllable, deterministically controllable, to enable this STDP with different functional forms, tunable in terms of time response and much lower variation, which means more reliable. And having achieved this then is exciting for enabling more biorealistic and also more energy efficient networks that are called spiking neural networks. And lastly, the third example that I want to give is what's even further beyond, right? So the nearest term context, as I said, is hardware DNNs. Get me the conductances that you're programming extremely fast with extremely low energy and repeatable. Next phase is the spiking neural networks, which are more energy efficient, but you need to be able to capture these local nonlinear learning rules, which we are showing that we can achieve with these electrochemical devices. But our neuroscience colleagues have many things to say, that of course whatever is being pursued in DNN and even in SNN is not really how the brain learns. And there are very exciting studies that our neuroscience colleagues are extracting for trying to understand how we learn. And one of those colleagues that we are lucky to have at MIT is Michael Fee, and he has been spending years, decades, experimentally trying to extract how songbirds learn to sing. And according to him, this learning rule has also resemblances to how humans learn to speak or other biophysical forms of learning. And he should be here to tell you this very beautifully, but in very simple terms, what it includes is the following. So baby birds, they're born like humans, they don't know how to speak, they don't know how to make good melodies, right? And they listen to their father and store what they hear in a certain part of their brain that's referred to as the context, that's stored in some tens of milliseconds bursts of the melody. And then they babble, just like we do, to try to emulate some of those songs, and that's referred to as the variability. So you have the context signal, that's the stored part of the melody, and the babbling, that's variability introduced to the system. So at some point in time, if this variability matches a stored piece of the melody, that's condition one. So you made the right sound with a number of your vocal cords, but that's not sufficient to strengthen that synapse that control those vocal cords. There must also be a reward signal. And it could be some feedback from nature, it could be the father nodding his head, I don't know exactly, but there must be a reward signal. That's the third signal that must be coincident with the context and variability matching. And if all these three factors are coincident within a certain period of time, then the synapses that controlled those vocal cords to generate the right melody are strengthened. Okay? So that's why it's referred to as three-factor learning rule. What's key here is we know how to control the synapse, as I have shown to you in the previous slides, but how do we generate this control circuit around the synapse? And originally we thought we could do this with a semi-digital circuit, but we were prompted by Michael to think ionic because that's how it takes place in the biological medium. And indeed we can do that with the same electrochemical device, but running rather volatile to generate what's called an eligibility trace. So when in neuroscience field, when that stored context signal and variability introduced match, the local behavior generates what's called an eligibility trace, which makes that region eligible for being rewarded and strengthened. And again, the understanding in the neuroscience field for the functional form of this eligibility trace looks like this. It's an increase and a decaying transient in time. So the question is, can we generate this behavior for the earlier part of that circuit? And indeed, we can, because these are nonlinear devices, like we have shown in the STDP, plus we know how to operate them volatile by not floating the gate. We can come up with something like an AND plus delay operator by simply running these electrochemical devices volatile. And the resulting signal from that eligibility trace generation can then be overlapped with the presence or absence of a reward signal to ultimately decide what will happen with the synapse. And here is an example where, again, we're looking at the same electrochemical device, but in volatile form now. If the context and variability signals match in time, so they fire together, they overlap, then we can generate a non-zero signal, eligibility trace, which increases and decays over time, which qualitatively looks like the signal described in neuroscience field. And if the two signals fire apart, if they don't overlap, the output is non-linearly weaker, and you don't generate an eligibility trace. So that's step one. And if we then take this, where we have the eligibility trace, the context and variability overlap, and reward signal comes somewhere between this time period, then we can generate a non-zero potentiation or conductance increase at the synapse that's being fed to together with the reward and eligibility. And depending on where the reward comes, if it's closer to this peak, the strengthening is stronger. If it's too late, strengthening is either very weak or not there. Alternatively, if there was no eligibility trace, so there is no match between the stored melody and the babbling variability, even if you have a reward, it shouldn't be correlated to this failure, and there is no strengthening of the synapse. So this is one demonstration of a biorealistic learning rule that we emulate, a local learning rule that we emulate with an all-ionic circuit, which is very exciting because it gives us not only the biologically plausible response, but we're also able to do this with a very simple footprint, just two electrochemical devices, and compared to current CMOS and GPUs, it can be much more energy efficient. It may not even be able to capture this type of nonlinear coupled behavior trivially with CMOS. Good. So with that, I will end by repeating that these electrochemical battery-like devices, so miniaturized low-energy, low-capacity battery-like devices, give us the ability to deterministically control electronic conductivity of a target material. And if you choose the right type of materials, you can scale them down, you can make them CMOS compatible with extremely low energy, and you can push it down to very fast speeds. But to be able to achieve both of this with compatible voltages, to integrate them with circuit drivers, you still need better understanding of these ion conducting, in particular here, proton conducting electrolytes and interfaces to push those to become faster. And the concept that we are pursuing here is potentially an enabler, a low energy building block for more biorealistic, more capable AI hardware that we can leverage not only in the near term for DNNs, but also in the medium and longer term for spiking neural networks and even more bioplausible systems like the Songbird model that I have shared with you. So with that, I will stop here and see if you have questions.
Thank you very much, Bilge.
Thank you.
Now, any questions? We need to get a mic.
Thank you, Bilge. Wonderful talk.
Thank you.
Very inspiring. I was wondering about the electrolytes you mentioned that sort of are grain boundary electrolytes that, well, are not, well, so it's expected that they are proton conducting at their surface, if I understood correctly. Proton conducting,
Yes.
sorry. So I was wondering, so typically these systems need a kind of water surface layer to be reasonably conducting. So maybe you can comment on how this requirement can be integrated with the type of systems you've shown. And then the next question would be, why not using a liquid electrolyte? Is that something that you've been considering?
Yes. So with those nanoporous, disordered, low-density systems, indeed, you need the absorbed OH layers at the least. And in proton conductivity field, this is typically done by controlling the humidity, showing that conductivity goes higher by going to higher humidities, and we do that separately for conductivity measurements. But with these devices, it's whatever adsorbed ambient. So ambient OH that's absorbed in this nanoporosity during preparation in the case of PSG, or just ambient exposure with the hafnia and zirconia layers, that's giving us some proton conductivity, but still very low, like order of 10 minus 10, in fact, when we look at it, without controlling humidity. That's why we need to go to very high fields to get reasonable speed out of them. So the role of OH and water is there, but for practicality of these devices, we don't increase humidity as we try to control the electronic conductivity. So liquid electrolytes are of course possible, but then it's less practical to do devices with. So for scientific studies, I'm all for that, and we are also doing ionic liquid studies because they have faster proton conductivity through them. But for miniaturization, both in vertical and lateral directions, you need some inorganic fabricatable material. And these are those type of materials, but they are bad proton conductors. So we have a line of separate research where we are studying just proton conduction mechanisms, physical descriptors for them to be able to come up with better proton conductors that are inorganic. That's a challenge for the field. So I'm very excited about it and we're pursuing it, but others should also, beyond just microstructure control. How can we make inorganic materials better proton conducting?
Perhaps a quick comment. I mean, when you look at the field of, let's say, biological systems, synaptic systems, and so forth, there you would actually think of, let's say, liquid electrolytes.
Exactly. Our brain is liquid electrolyte.
Exactly.
Yes.
Exactly. So the whole, body basically runs on liquid electrolytes,
yes.
right? So I was wondering if, in the long run, you actually need liquid systems rather than the solids you've been describing, simply because,
So I think that's a fair question. Depends on the application. If you don't have to miniaturize and make a large area compliable structure for a bio-related integration, maybe you don't need to miniaturize and you can work with enclosed liquids. For this application, it's better not to work with liquids.
Thank you.
Yes.
Maybe ionic liquids.
Exactly. Ionic liquids we are pursuing just for the science of this interface exchange reactions. Yes.
There's a question from Natalie.
Yeah.
Or, no, from Stephen, is it?
Hi, nice talk, thank you.
Thank you.
One of your slides showed that one of your desirable constraints was an ionic conductivity bigger than 10 to the minus 4
Yeah.
Siemens per centimeter.
Yes.
which is going to be tricky for protons.
For protons, it doesn't
yeah,
exist
it
other
doesn't
than
exist.
Nafion.
I know,
Yes.
right.
Yeah.
So have you thought about silver? I mean, rubidium silver iodide's got a conductivity of 0.1.
Yes. So
I
there
imagine you
are
get silver
like
into...
superionic conductors for silver. Another constraint, and you're right, like the whole, that analysis is ion agnostic. So if you want to make a similar electrochemical device with silver, I'm not sure about the interface exchange, but at least the electrolyte conductivity is there. A constraint that we had here, because our original sponsors were from industry, was to consider ions that are CMOS compatible. So silver, lithium, sodium, these are not, they don't want to hear about it because they are so mobile that they go and poison other components in the line. And that's why we try to constrain ourselves to more benign ions like proton and magnesium. But those values, as we reported as target, are ion agnostic. And if there is an application where silver is much welcome for this type of analog computing for AI, at least the electrolyte conductivity is there. It's there also for lithium. But again, it's not desirable for the CMOS. Yes.
Oh,
Or maybe that question was earlier. Yeah.
do we have a mic?
To add a reward signal, you mentioned that we need AND gate or delay. So how we can introduce a delay in ion channel?
Yes, so I call that circuit as if it's an AND plus delay operator, because AND is when the two signals overlap, the response is exponentially stronger. And delay is because we are running that device volatile. Once the pulse goes off and you didn't float the gate, the system goes back to the original equilibrium and decays back. So there is a time period that is the transient, that's like delay after the overlap, and that's why I refer to it as if it's like an AND plus delay operator. But the delay is the transient.
This how can we introduce this in ion channel?
In what?
In ionic device?
Yeah, it is the device. So it is the battery device. You send the pulse voltage. Once the pulse is gone, like past, it goes back to the original state. As long as you don't float or open the electronic path, it goes back to the original equilibrium. And how fast it goes, of course, depends on, again, the material properties. Yes?
Hi, I'm a little bit puzzled. Basic question is what the optimum conductivity of the channel would be, because I know that one of the current champions in neuromorphic memories is probably phase change memory, and there people work with tens of kiloohms or kiloohm range. You're working at sub-gigaohm range. At the same time, you say extreme energy efficiency. I can't put together those two.
Yes.
What would be the optimal? Obviously, it's the best when there is no conductivity at all, and then some conductivity. But what this some conductivity should be, kiloohm range, megaohm
so for
range?
like a 10 nanometer by 10 device, you need to be in the nanosiemens regime. So the high resistance should be really high. And then you modulate within about 10-fold of it at the least. So there is a cap on how high conductance you can go. And that is at least determined for, again, the hardware DNN context. For SNN or for these other devices, I expect you still need very low resistance, but I cannot quote a number for them. And again, for hardware DNN, we do achieve that very low resistance to start with and modulate within an order of magnitude out of that. And the low energy comes from not the voltage, but extremely low gate currents we are working with. So, for example, tungsten oxide is very sensitive in terms of its electronic conductivity to ion insertion in the in the very low concentration regime. So it's like every pulse is just tens of protons that we get the discernible states with. So voltage is high. We are working at the very low resistance where the material is most sensitive, and that allows us to use very low gate currents, because gate current means also proton current.
So it's essentially voltage squared divided by resistance of the channel. This is how you calculate.
We know the voltage, we know the gate current, and you get the energy from voltage and current.
Well,
because it's not the resistance of the channel, it's the writing voltage. That has to be the resistance of the whole device. But the channel resistance is very low to start with.
So is the extreme sensitivity of the tungsten oxide to conductivity of the hydrogen concentration, is that really a good thing? Because it means that you may have more variability from device to device, because it's going to be hard to exactly control the amount of protons, right?
You would think so, but because the conductivity modulation is through this in-gap state, as I mentioned. If the in-gap state position stayed the same, it should have been linear, but it actually moves up with increasing proton concentration. And that stronger than linear sensitivity comes from the moving of that in-gap state. And because it's intercalation, it's not microstructure that's involved in that concentration regime, then it's actually much more repeatable than if it were some extended defect dominated.
Okay.
So actually it's a good thing, because you need that extreme sensitivity so you can work with small proton currents or small gate currents.
Well, please join me in thanking Bilge for an excellent lecture.
Thank you.